Hello everyone. In this video, I will be talking about work done by a variable force and potential energy. Now, work done by a variable force. In our real life, mostly all forces are variable. This is a graph showing the force to displacement. That is, this is a force displacement graph. And here it is shown that the force is varied when the object is displaced from xi to x. Now, in order to find the total work done, we will first split this whole into very small sections of area delta A, which is equivalent to f of x into delta x. Now, if displacement delta x is very small, then force is constant. So, we can use the formula for work done, that is delta W is equal to f of x into delta x. Now, total work done can be equivalent to the sum of all the areas shown in this graph. That is equivalent to sigma from xi to xf, f of x into delta x. If delta x tends to 0, then W becomes limit delta x tends to 0, sigma of xi, xf, f of x into delta x, which is equivalent to integral of f of x dx from xi to xf. So the work done by a variable force is given by the integral of the function of force and the displacement from xi, which is the initial position, to the xf, which is the final position. Now, work energy theorem for a variable force. Time rate of change in kinetic energy is here. It is given by the differential, that is dk by dt, or dy dt of half mv square is equal to m into dv by dt into v. We know that dv by dt is equal to acceleration, and from Newton's second law, mass into acceleration is equal to force, which becomes F into v, and v is given by the differential, that is the rate change with respect to displacement, that is dx by dt. Now, from this we get dk is equal to f dx. Now, integrating both sides from initial to final, that is from initial kinetic energy to final kinetic energy, that is kf, and from initial position to final position x, we get kf minus ki is equal to integral of xi to x of f dx. We have already seen that integral of xi to x of f dx is the total work done by a variable force. Hence, kf minus ki is equal to w. Now, we can see in detail the concept of potential energy. Potential energy is the stored energy by virtue of the position or configuration of a body. The body left to itself releases this stored energy in the form of kinetic energy. For example, a body kept at a height possesses potential energy by virtue of its position. For example, the dams used to produce electricity in hydroelectric projects use the potential energy of the stored water. And when the stored water is released, this potential energy is converted to kinetic energy, which is used to rotate the turbines to generate electricity. Similarly, the potential energy stored in a compressed spring. When the spring is released, it is converted to kinetic energy. Now, it is given by mgh for a body kept at a height h from the ground, where mg, which is the gravitational force acting on the body, and h is the height. If the height h is very small compared to the radius of the earth. Now, we can consider this is a table and a body which is at first at the ground is raised to the height h and kept above the table. Then this work done against gravity to raise this body to this height of h is minus mgh, since mg is the weight of the body acting downwards, or the force applied by the gravity on the body of mass. So we can express potential energy as a function of height as V of h is equal to mgh. Here V is used to denote potential energy. Now, if this body is allowed to fall down this same height, then from the equations of motion, which is v square minus u square is equal to 2as, v square is equal to 2gh. Since the initial velocity is 0 and a is equivalent to the acceleration due to gravity, which is g. So v square is equal to 2gh. On multiplying both sides by mass, we get half mv square is equal to mgh. That is, kinetic energy is equal to potential energy. That is, the potential energy of the body of mass m kept on the table is released as kinetic energy when it falls towards the ground. Now, conservation of mechanical energy. The total mechanical energy of a system is conserved if the forces doing work on it are conservative. Gravitational force is a conservative force since the force only depends on the final and initial position of the body, as we have already seen in the case of the falling mass in the previous example. Now, by work energy theorem, for body undergoing displacement under conservative force, delta k is equal to f of x into delta x, and potential energy function Vx can be defined such that negative delta V is equal to f of x into delta. So from the above equation, we can see that delta k plus delta V is equal to 0, or delta of k plus V is equal to 0. This means k plus V is a constant throughout the whole path. Hence we can say that Ki, which is the initial kinetic energy, plus potential energy of the body at initial position xi is equal to kinetic energy possessed by the body at the final position plus potential energy possessed by the body at the final position. This is the conservation of mechanical energy. Now, potential energy of a spring. The spring is an example of a variable force which is conservative. The spring is light and may be treated as massless. In an ideal spring, the spring force Fs is proportional to x, where x is the displacement of the block from the equilibrium position. By Hooke's law, the spring force is given by Fs is equal to minus kx, where k is a constant of proportionality having a unit of Newton m raised to minus 1. Now, this is a figure showing different position of the spring. At first, the equilibrium position of the spring is shown. In second, the stretched spring is shown, and the third figure shows the compressed spring. The second case, Fs is negative and x is positive. That is, displacement is positive. And in the third case, that is when the spring is compressed, the spring force is positive and the displacement is negative. This is a displacement force graph drawn. From the area of this, we can find the work done by the spring or the potential energy of the spring. That is, Ws is equal to integral of 0 to xm, where xm is the displacement, into Fs into dx, where Fs is the spring force. That is equal to minus kx by Hooke's law. On substituting that, we get Ws is equal to minus kxm square by 2 in the case when the spring is stretched. Similarly, in the case when the spring is compressed, the spring work done by the spring is positive kxm square by 2. And similarly, the work done on the spring is negative kxm square by 2. And in the first case, it is positive kxm square by 2. So this is the end of this video. In this video, I have discussed work done by a variable force and potential energy. If you have got any doubt in any of the concepts discussed in this video, please comment in the section below this video. Thank you.